This is a video on Z-transforms. It deals about the basic understanding of Z-transforms and the region of convergence. What are basically Z-transforms? They are the discrete counterpart of the Laplace transform. We can apply a complex exponential input to a LTI system. Under such a case, a signal x of n is equal to z power n would be produced, and such a signal could be represented as z is equal to r e power j omega, which is a complex number whose magnitude is r and angle is omega. X of n thus could be represented on substitution into this particular expression, the value of z is equal to r e power j omega as x of n is equal to r power n cos omega n plus j into r power n sin omega n. Thus, the real part of x of n is an exponential damped cosine, and the imaginary part of x of n is an exponential damped sine. The positive number r determines the damping factor, and omega is the sinusoidal frequency. X of n is a complex sinusoid if r of n is going to be equal to . Let us go on to consider the definition of the transfer function in the case of Z-transforms. H of z is going to be equal to k equal to minus infinity to plus infinity h of k z power minus k. The Z-transform of an arbitrary signal is given as x of z is going to be equal to summation n equal to minus infinity to plus infinity x of n z power minus n. The inverse Z-transform is given as x of n is going to be equal to 1 by 2 pi j integral x of z of n minus 1 dz. Therefore, the relation between x of n and x of z is thus established in this particular discussion. X of n could be translated into x of z. Similarly, we could also translate x of z into x of n. Thus, the signal x of n is a weighted superposition of complex exponentials given by z of n. The weights are given by 1 by 2 pi j x of z minus 1 dz. Such an integral need not be evaluated. It requires the knowledge of complex variable theory, which makes it more complicated. Thus, the evaluation of the inverse Z-transform is generally done by inspecting the one-to-one relation between x of n and x of z. Thereby, we could convert x of n to x of z and x of z to x of n as discussed in the previous slide. Now, let us go on to the discussion of the Z-plane. The Z-plane is somewhat similar to the S-plane that is discussed usually in the Laplace. Here, the Z-plane is generally a unit circle whose actual radius is r, which could be reduced to 1 in a normal case. Thereby, if the radius is r, we could represent it as z is equal to r e power j omega, where omega is the angle generated by a point of z with the real axis. Thus, the point z is equal to r e power j omega is located at a distance r from the origin and at an angle omega with respect to the real axis as discussed earlier. Thus, for z is equal to r e power j omega, we could assume r is equal to 1, thereby giving it into a complex number as z is equal to e power j omega. Thus, x of e j omega is equal to x of z if z is equal to e j omega. This makes us realize that this expression is almost similar to the DTFT expression that we have discussed in the previous unit. Let us just see the relation between the Fourier transform and the Z transform. The Fourier transform is given by the expression x of e j omega is equal to summation n equal to minus infinity to plus infinity x of n e power minus j omega n, and the expression of the Z transform is x of z is equal to n equal to minus infinity to plus infinity x of n z power minus n. If x of n is absolutely summable, DTFT is got from the Z transform by setting r is equal to 1 and z is equal to e power j omega. In other words, the system needs to be stable in order to apply the DTFT conversion from the Z transform. DTFT is applicable only to stable LTI systems, and it means that it exists only if the impulse response is absolutely summable. The Z transform, on the other hand, exists for unstable system also, which means it does not require the condition of x of n being absolutely summable or the impulse response to be absolutely summable. Let us go on to understand a simple example of a Z transform given a sequence x of n whose values are 0, 2, 4, 6, 4, 2, 1 for indices of n minus 1, 0, 1, 2, 3, 4 and 5. Such a case could be written as the Z transform is equal to, for negative values of n, we have seen that the value of x of n is 0. It starts from n equal to 0. The first valid coefficient is 2. Therefore, it is going to be 2 plus 4 into z minus 1 plus 6 into z minus 2 plus 4 into z minus 3 plus 2 into z minus 4 plus 1 into z minus 5. Therefore, the instances of 1, 2, 3, 4 and 5 are converted to indices minus 1, minus 2, minus 3, minus 4 and minus 5. Here also the indices will be z power minus 0, which is equal to 1, thereby resulting in x of z is going to be equal to just the constant 2. The same could be converted into the DTFT, assuming the expression to be absolutely summable or the system to be stable, resulting in x of e j omega is going to be equal to 2 plus 4 into e power minus j omega plus 6 into e power minus j2 omega plus 4 into e power minus j3 omega plus 2 into e power minus j4 omega plus e power minus j5 omega. This is exactly the conversion from the Z transform to the DTFT, which appears to be quite simple if it satisfies the absolutely summable condition. Let us consider one more finite length sequence given by the normal representation 1, 2, minus 1 and 3. At n equal to 0 it is 1, resulting in a Z transform of, on similar grounds, 1 plus 2z minus 1 minus z minus 2 plus 3 into z minus 3, as could be obtained from 1, 2 and 3, giving 2 into z minus 1, minus 1 into z minus 2 and 3 into z minus 3. Next, let us consider a normal system representing y of n and x of n with some coefficients like y of n is equal to 6 into x of n minus 5 into x of n minus 1 plus x of n minus 2. What could be the Z transform of such an expression? It is given by h of z is equal to 6 minus 5z minus 1 plus z minus 2. Reason being, for x of n, we would be writing it as z power 0, here it is z power minus 1, here it is z power minus 2, and so on. Let us consider how the Z transforms could be represented. The real part of x of n is an exponential damped cosine, and the imaginary part of x of n is an exponential damped sine. Here, a signal has been plotted whose r value is 10 and omega is 2 pi by 5 for both the cosine signal as well as the sine signal. The damped cosine and damped sine signal has been shown here for r equal to 10 and omega equal to 2 pi by 5 as given here. The cosine signal moves like this and it tends to decay, and a time value of up to 0.1 is shown here. Similarly, in the second case also it is a damped sine which is again plotted, and this is also exponentially decreasing in its value. And since n is equal to 5, we can see that at each period we have 5 values. Thus, r determines the damping factor, which means the damping rate in this case is 10, and omega is the sinusoidal frequency given by 2 pi by 5 as can be seen here. X of n becomes a complex sinusoid if r is equal to 1, as can be seen from the expression here. Actually, x of n is r power n cos omega n plus j sin omega n. When r is 1, it becomes 1 power n, which is 1. So x of n is cos omega n plus j sin omega n. And this is equivalent to a complex sinusoid. As mentioned here, it is equivalent to e power j omega. Let us consider the plots of z power n at various points on the z plane in order to get an idea how each point would look like. Let us first consider the plot on the unit circle. It would look like a point here where it is a pure sine wave. We could also consider another plot which is lying somewhat inside the unit circle, resulting in a damped signal like this. Similarly, a point outside the unit circle, as shown here, would look like a rising damped signal. Thus, various points can be imagined at various points on the unit circle, and the resulting signal could be generated by substituting in the expression of z is equal to r power n cos. Let us try to understand the concept of convergence with respect to Z transforms. The Z transform exists when the infinite sum in the expression x of z is equal to summation n equal to minus infinity to plus infinity x of n z power minus n converges. The necessary condition for convergence is absolute summability, as could be seen from the previous cases where we have discussed the concept of stability for linear time invariant systems. Hence, x of n z power minus n's absolute summability needs to be analyzed. And since the value of z, that is r e power j omega, is equivalent to r power minus n, we could substitute it as x of n z power minus n would be equal to x of n r power minus n, resulting in the absolute summability expression requirement as n is equal to minus infinity to plus infinity x of n r power minus n is less than infinity, because z is equal to r e power minus j omega. So we have substituted the value of r, resulting in this particular condition for summability or for convergence. Thus, we can easily define the range of r for which this particular condition is satisfied, and it is this range of r which is defined as the region of convergence of the Z transforms. In other words, the Z transform is valid only for the region of convergence. Hence, it is very important to evaluate the region of convergence along with the Z transform evaluation. let us now go on to consider the region of convergence. The region of convergence can have various conditions based on the sequence. First, let us consider a sequence which is left-sided, which means it lies on the negative side of n equal to 0. Under such a case, we would be getting the sequence as all points. If this point is A, we would include all points inwards from z is equal to A towards z is equal to 0. Similarly, for a right-sided sequence, which is the normal sequence, where we assume that the right-sided sequence has a pole which lies at B, the region of convergence would be all points outside the point B as shown in the grey region. Similarly, for a two-sided sequence which may have B and A chosen such that Z lies between B and A, we would see later that the region of convergence now reduces to a strip whose radius lies between B for a right-sided sequence and A for a left-sided sequence. Thereby, this would be B and this would be A. Next, let us try to understand the Z-transform table, at least the basics, which may be necessary for understanding some simple problems. Let us go on to start with the value of x of z and its equivalent r of c, because only for r of c the definition of x of z would be valid. We go on for the first definition, which is an impulse function, which is going to be valid as x of z is going to be equal to 1 for all z. Similarly, for u of n, it would be 1 by 1 minus z minus 1 when z is greater than 1. This is actually a right-sided sequence which lies from n equal to 0 to infinity, that is on the positive side of n. Similarly, for a left-sided sequence which is given by a delayed unit step u of minus n minus 1, we would see the Z transform is identical to u of n, but the region of convergence changes. It is Z lies less than 1. We would also consider one more Z transform, which would be an extension of the first one, u of n. Here it is a power n u of n, which will be seen frequently in problems. It is given by 1 divided by 1 minus a z minus 1 on the condition of the region of convergence similar to u of n, as modulus of z would be greater than a. Let us consider that in general the Z transform is an infinite sum. In other words, the Z transform may not exist for all values of z, and thus we understand that the value of r is equal to modulus of z is the most important part for understanding the region of convergence. Let us go on for a simple problem given by x of n is going to be equal to 0.5 power n u of n. In such a case, x of z would be equal to n is equal to 0 to infinity 0.5 power n z power n as per the definition of x of z, resulting in n equal to 0 to infinity summation 0.5 z power minus 1 power n. On the basis of the Z transform table, it appears as z divided by z minus a, resulting in 1 divided by 1 minus 0.5 z minus 1. This is actually a right-sided sequence, so we would see that the region of convergence lies outside 0.5, resulting in a region of convergence beyond 0.5, where we have considered a unit circle of 0.5. Sorry, not a unit circle, it is a circle whose radius is 0.5. So the region beyond this would be considered as the region of convergence for this particular problem. As shown here, this would be the region of convergence, what is shown in white, beyond 0.5. Let us go on to one more problem to determine the region of convergence for a problem given by x of n is going to be equal to 1 by 4 u power minus n. From the definition of the Z transform, x of z is going to be equal to n equal to minus infinity to 0, 1 by 4 z power minus 1 n, because we have got minus n, the summation moves from minus infinity to 0. This could be rewritten as summation n equal to 0 to infinity for z power n, and the resultant would be 1 divided by 1 minus 4z using the Z-transform table, a power n u of n, and the region of convergence would be modulus of z is less than 1 by 4. Thus, we would see that since it is a left-sided sequence, we need to identify which is 1 by 4. We have identified the unit circle here. This is our pole which is lying at 1 by 4. So the region of convergence is all the place inwards from 1 by 4 to z equal to 0 as shown in black region here. Let us go on to one more problem to determine the region of convergence for a similar problem given by x of n is going to be equal to 2 power n u of minus n minus 1. Here, extending the definition of the Z transform, x of z is going to be equal to n equal to minus infinity to minus 1 summation 2 power z minus 1 power n. This results in a rewritten form as n equal to 1 to infinity 1 by 2 power z power n. The Z transform of this particular expression, as can be seen, is similar to the expression a power n u of n, resulting in 1 by 2 power z, 1 by 2 into z divided by 1 minus half power z. Let us multiply the numerator and denominator by 2z minus 1, resulting in minus 1, 1 minus 2z minus 1, and we would see from here that the region of convergence is z modulus is less than 2, and since it is a left-sided sequence, we would see that we needed to identify the pole which is lying at 2, and all points inside the circle from till z equal to 0 would be the region of convergence. The unit circle is shown in dotted line in the red color. We will go on to the last problem to determine the region of convergence given by x of n is going to be equal to 2 by 3 power n. From here, we should understand that it is modulus of n which is given here. So the modulus of n would be positive, means x of n is positive, which means from 0 to infinity, and n is negative, which means x of n would be negative from minus infinity to 0. Therefore, the expression could be rewritten as x of z is going to be equal to, from n equal to minus infinity to minus 1, it would be taking the minus, removing the minus sign from here and putting it here, 3 by 2 z power minus 1 plus summation n equal to 0 to infinity, the usual expression 2 by 3 z power minus 1. Therefore, we would be getting this expression as, on similar grounds to what we have, for x of n is equal to 2 power n u power minus n minus 1. We have got this as half z, 1 minus half power z. Just in the previous slide we have discussed it, resulting in a value given by minus 1 divided by 1 minus 2z minus 1. Here, similarly, this particular problem is similar to that, resulting in minus 1 divided by 1 minus, since it is 2 power n here, it is 3 by 2 here, 3 by 2 z minus 1, and naturally we would see that the region of convergence also would be less than 3 by 2, plus this is a normal Z transform which is going to be given by 1 divided by 1 minus 2 by 3 z power minus 1. And as mentioned here, the region of convergence is modulus of z is 3 by 2, less than 3 by 2, as in the previous problem modulus of z is less than 2, and for this case it is modulus of z is greater than 2 by 3. Therefore, the region of convergence we would see is going to be a strip, as has been discussed in the previous cases of a two-sided sequence. This becomes a two-sided sequence as the values of x of n exist both from minus infinity to plus infinity, which means from 0 to plus infinity, and from -1 to -infinity, resulting in a two-sided sequence giving rise to a strip as the region of convergence lying between 2 by 3, which is going to be the region beyond 2 by 3, and here it is 3 by 2, the circle inside. So the common area is considered as the region of convergence. So some area which is there inside this part is removed, which is belonging to 3 by 2. Therefore, the region of convergence lies between 2 by 3 and 3 by 2. And on solving this and converting it into a better form, we would be getting the solution as minus 5 by 6z into z minus 3 by 2 into z minus 2 by 3. Thus, the region of convergence lies between the modulus of z is going to be between 2 by 3 to 3 by 2, resulting in a two-sided sequence, as can be seen in this particular problem. Let us go on to the references, which are as usual Oppenheim and Haken.